The important difference here is that every effort made in manufacturing, so even if it leads to the increase of 1% yield, if this is an increase of 1% yield of every single batch throughout the full product lifecycle, this is a huge business benefit. So I would say that I'm a big fan of modeling, and I strongly believe modeling brings value throughout the full product lifecycle. But what we know is that the closer the model sits to manufacturing, the higher the return of investment is.
You've got data everywhere, upstream, downstream, analytics, scattered across systems that never talk to each other. What if that mess is actually a gold mine you haven't tapped yet? Today's guest, Ignasi Bofarull-Manzano, who's a senior data scientist and CMC consultant at Körber Pharma, shows how digital solutions and digital twins unlock that value. Faster development, more robust processes, and higher productivity. Let's dig in. Are you juggling the complexities of CMC development while trying to enjoy the beauty of biotech? Have you ever wondered if there's a way to simplify bioprocessing? Welcome to the Smart Biotech Scientist podcast, where we're diving headfirst into the very challenges you face. We're breaking it down, demystifying the jargon, and giving you the keys to unlock your full potential. I'm your host, David Brohlman, and I get it. With 15 plus years in the biotech industry, I face the same challenges you do. There's a way to simplify and streamline so you can remove complexity, you can skip trials and errors, deliver without delay your groundbreaking therapy to clinics and market, and still enjoy every single step. Do you want to learn how industry experts and I did it? Grab a cup of coffee and your favorite notebook and pen. Now is the time to take your bioprocessing game to the next level. Let's smarten up biotech. Welcome, Ignasi. It's good to have you on today.
Thank you, David. Glad to be here. Very excited.
Let's start our conversation with perhaps this controversial question. Share something that you believe about bioprocess development that most people disagree with.
I think many people overestimate what is required to build a digital twin in bioprocessing. They assume that usually a lot amount of data is required, as well as you need very fancy models, but neither is necessarily true. So probably we will talk about modeling a lot throughout this podcast, but when it comes to the data requirement, so in our industry, we have actually a lot of data because data is spread throughout Excel files, historians, ELNs, MES, analytic systems, etc. For me as a data scientist, I'm always happy to have more data because basically I don't want to miss any important source of variability. But when it comes to implementing digital twins that bring benefit, the essential question is what decision should the model support and therefore which data are needed for that context of use. What does this mean in plain language? So for example, we have several published use cases where the typical data that you have from process validation together with handful of manufacturing runs have been enough to build a useful end-to-end digital twin in manufacturing. So what matters is the type of data. For example, many people focus a lot in product amount, but they don't measure quality. And for example, it's also very important that you investigate during your process validation starting material variability. So it's not so much about data quantity, but it's more important data quality.
You're making several good points, and we're going to unpack these various points during our conversation. I'd like to first talk about yourself. Draw us into your story. What was the spark that attracted you to science and then eventually to data science, modeling, digital twins, and what were some interesting pit stops along the way?
So since I was very young, I've always have like a spark for curiosity. So in many diverse fields, and of course, biology, it's been the most important field that spark more curiosity in me because we all are a human life, so we all get sick, etc. So for me, it was clear I wanted to study something related with biology. At the same time, however, I've always been a lot into mathematics and numbers. And even though I have a huge curiosity to understand how things work, I also like to get things done. So I've always been a lot into the application of things. So this is how I came across biotechnology. And so I did both my bachelor's and master's in biotechnology. At the very beginning of my bachelor's, I had point actually where I was even hesitating to stop biotechnology, because what happened to me is that from the theoretical point of view, I like it a lot, what I was studying. But for example, I didn't really like being in the lab. So it was a trade-off that made me hesitate whether stopping. But the third year of my bachelor's in Barcelona, I had the bioreactors subject, and then I saw that this was very applied. And also it was a first step somehow into modeling. We could call it like very simple modeling. So like just mass balances, for example, how much you have to inoculate your reactor, when you should stop the fermentation, etc. But it was already a motivation to delve deeper into this field. And when I really discovered that modeling was really my thing is when I did my master thesis in a startup in Vienna about hybrid modeling. And then is when I realized that I love it and that it was really my place to be. Let's call it like this.
Yeah, fantastic. Let's start with the buzzword. A lot of people talk about digital twin these days. And then when you look into what it actually means, you realize that it means different things for different people. So what is actually a digital twin, or what separates a true digital twin from, I'd say, a fancy dashboard or a simulation?
So a digital twin, as I understand it at least, is primarily a concept referring to connectivity to the physical process and the data decision loop, rather than a particular mathematical model. So the model running in the background can be statistic, mechanistic, or hybrid. So one useful way to explain the different maturity levels is to distinguish between a digital model, a digital shadow, and a digital twin. So at the first stage, we have a digital model, which is basically a mathematical model running on a computer and fed using historical process data. It can already be very useful for process development, simulation, and optimization, but it is not yet connected to the physical system. The next step that we have is to bring shop floor data into the model. Once the model receives near real-time data from the physical process, we move toward what people call a digital shadow. And now the model can follow the batch as it processes, predict product quality, and issue early warnings, for example. Finally, if we are able to close the data loop so that the model's predictions or recommendations are communicated back into manufacturing workflow and influence the physical process, this is what, according to the definition, is called a digital twin. So this bidirectional data flow is very important. And there is actually an example I like to use to make this easier to understand, which is Google Maps. So imagine that tomorrow you need to travel from A to B, and a static route planner can calculate a route based on distance and typical traffic patterns. However, you have your route plan, but tomorrow when you start the journey, traffic, roadworks, or accidents may change the best route. Google Maps receives this live information, recalculates the prediction, and recommends a new action. Then you as a driver still are in the loop, so you have the decision to take the recommendation or not. But if you take the recommendation, basically this is influencing how you interact with the physical world. So then in this case, Google Map would be used as a digital twin. And the same principle basically applies to manufacturing. When we set up a control strategy, we define set points, which ideally are the optimal or best route. But we know that in reality, when we have real process variability, the optimal route might change. So a digital twin is responsible to interpret this variability in real time and suggesting the optimum new route if it has changed.
Now, to build a digital twin or to build just a model, I'd say more of the earlier stages of what you've outlined, we need a lot of data. And you also mentioned that in the beginning, it's not only the amount of data, it's the quality of data. So what I'm observing is that a lot of biotech companies have huge data silos because of legacy systems, because of different histories of sites, because of different mentalities, a lot of reasons. Where do you even start as you're developing, I'd say, a more digital development approach and hopefully at the end of the day, an end-to-end digital approach?
Yes, a good question. So We have a lot of data, as you said, and in an ideal world, we would use all this data to fit a product lifecycle digital twin. However, this is, for me as a data scientist, the dream, but this is not actually the reality. So what happens, as you said, is that the bigger the company is, the more data chaos they have, because they have many employees across many departments, sites, countries, and also systems. So what is important is first, instead of aiming for Mars, try to go first to the moon. So first define the decision and the context of use of the model that you want to build. Based on this, you need to identify which data is required for that model context of use and which interfaces you need to connect. So you don't need, as I said at the very beginning, you don't really need all available data, but only the required data. And also what I recommend is starting small. First of all, you always need a business need, like what's the bottleneck? Is it a time to market? Is it manufacturing costs, etc.? Then identify the type of model that you need for that and the required data to get a reliable model that fulfills that context of use. Then still don't go fully in real time like a digital twin, because this also comes with some effort. So first build a model. It's also very important, by the way, building end-to-end process models. So facing the process, for example, that upstream is a bottleneck in your production process. It's still very important that you connect the model that you built in upstream with all the subsequent unit operations to really identify or evaluate if upstream is actually really critical for drug substance amount and quality. So start small, always try to go end-to-end or holistically, and offline show the business value. And only then, if there is a clear business value that these end-to-end process models offer, then scale, which means basically connect it to all the interfaces and systems to get the bidirectional data exchange.
So let me paraphrase this once again, because you've made an important point. Start with the end in mind. So what does the business need, or what are the bottlenecks of the business? And then focus on that. Don't try to solve 10, 20 problems at the same time. Focus on the most important ones. And then once you have a proof of concept, then you can further expand on that.
Exactly. You summarize it very well. And basically why I'm mentioning especially to first identify your problem is because I'm seeing in the last 2 years, especially with all this AI boom, that from some management, they mix digital twins with AI and all this, but they don't really have a use case. So it's just, this is a common first mistake I would recommend people not to do. So just don't start building models for the sake of building models and to sound sexy, if I can say.
From what you've seen, is there perhaps a certain area in bioprocessing where usually people start with because the business value is very clear, or is it more on a case-by-case basis?
It's on a case-by-case basis. It's true. And perhaps this is also one thing similar to your very first question of things that I might disagree with many people. So many people focus a lot in models for early or late stage development. And we also do this. And the numbers that you get there are more appealing. So for example, we have shown that you can save, for example, 70% of experimental efforts by using end-to-end process models during process characterization. So this is a big number, right? 70% decrease. However, you are still in process development. So actually, you might fail in clinical trials. So of course, there is a benefit. I mean, if you reduce by more than half your experimental effort, it's a big business value, especially in time. So usually in process development, the business benefit is faster time to market rather than saving experimental runs because are relatively cheap. So on the other hand, we have manufacturing. And there we've built models, either doing root cause analysis or these end-to-end process models in manufacturing. The business benefit, according in numerical terms, like is smaller. So for example, we have seen that with an end-to-end process model in manufacturing, we can increase on average the yield by 4%. So now if you compare 4% versus 70%, 4% is yield, 70% is number of runs, but you could increase in lab scale for 200 the yield. But the important difference here is that every effort made in manufacturing, so even if it leads to the increase of 1% yield, if this is an increase of 1% yield of every single batch throughout the full product lifecycle, this is a huge business benefit. So I would say that I'm a big fan of modeling, and I strongly believe modeling brings value throughout the full product lifecycle. But what we know is that the closer the model sits to manufacturing, the higher the return of investment is.
Yeah, I agree. Definitely in terms of monetary return on investment, that's where you're going to see a huge return on investment. Thinking or considering that you're going to produce your drug the next 10 years or 20 years, definitely. Perhaps I would say in development, the ROI can also be non-monetary because several companies have now increasing pressure on times of development. And if you can save efforts there and be faster, that's also a tremendous return on investment. I'm curious, for instance, for a smaller company where you have limited data because you're starting out perhaps or for other reasons, what is your advice there? What should they do?
So if you're a small company, actually, you might have an advantage, which is that you might have a competitive advantage, which is you are starting from scratch. So from the digitalization point of view, you can build competitive advantage there. So it's important to always have, some people say, data first mindset, but this is more about digitalization. So when it comes to modeling, especially if you don't have a lot of data, start small, and which means, for example, start making sure that every single experiment, which anyway you have to do, either for R&D or for process validation, you use models that, for example, you make sure that every single campaign you do, you can squeeze the most knowledge out of it by using, for example, the state-of-the-art DOE methods, for example. And then scale from there as you grow throughout the product lifecycle. I don't know if this really answered your question or was more into another direction.
No, that's good because, yes, as a small company, I would say I would agree with you that you have a competitive advantage because you can start out from scratch and you can start right first time instead of trying to rectify or to correct past decisions.
Exactly. Because also, on the contrary, like for very big companies, as we discussed earlier, so they have so many different systems, and even if they have the same system, it might be used differently in different countries because they have different people there. It's true that they have way more data, but this can also be counterproductive because you can get lost in the data. Not all data is required. So this is why it's very important to really focus on which data I need to fulfill the context of use of my model. And for the context of use of my model, first I need the business need. So what's my problem? Then which model, how the model fulfills this with its context of use, and then which data I need to train this model.
Yes, absolutely. Now, you're also working on AI-based or physics-informed AI, let's say like that. What does that mean exactly? And I would also be curious to hear your perspective on what is the potential of AI, because you alluded to that already. There's a lot of hype out there. What can AI really deliver in this space and what can it not?
Yeah, so first of all, the name of physics-informed AI, I have to mention it's a bit hype also. So especially now I'm mentioning this because now there is another concept, which is called physical AI, which this is, for example, a term Jensen Huang from NVIDIA always mentions, is like his favorite topic. So these are two very different technologies. So the physical AI, it's based on generative AI, and it's basically generative AI embedded into physical systems such as robots or autonomous vehicles. On the other hand, the more modest physical-informed AI or physics-informed machine learning, or also known as scientific machine learning, is basically a machine learning model that during the training process, you force it to obey to physical principles, first principles, mainly differential equations. And the main purpose of this is that once it's trained, the model will respect the physics. So what's the advantage of this? So this is twofold. On the one hand, it allows to combine data with first principles. So for example, in upstream, we cannot describe everything with differential equations. So we know it's not clear, for example, how pH influence cell growth. For example, we don't have a monod equation there. So these type of models allow to combine data with first principles. But actually, this is not completely new. Actually, there is a concept of hybrid model. Maybe we can discuss later. But it's still one advantage. The second advantage is that while they stick to the physics because you have been enforced them during training. Once the model is trained, you don't need the physics anymore. So basically what this means is that you don't need differential equations anymore. And this is a big advantage because some differential equations in partial differential equations are complex to compute. So basically they are slow or not as fast as we would like. And this brings a bottleneck, for example, to do uncertainty quantification in real time, or for example, solving the inverse problem, which means identifying the mechanistic parameters when you deal with high throughput data, for example.
What is the difference with respect to hybrid modeling?
So I would say that the philosophy is the same, which is combining data with first principles, so the information that we know, but how it's implemented is differently. And here it may be a bit difficult to explain without a whiteboard, but you could imagine, for example, the typical cell growth differential equation. So where X is the amount of cells. So you know that dx dt, which means the change in cell growth by time, equals to mu, a specific rate, multiplied by X. So we know this because it's kind of a logic equation. We know everything happens through cells. If there are no cells, there cannot be any cell growth, right? So a hybrid model, what it would do is, for example, as a function of pH, it would train a neural network where the neural network is predicting the specific rate, the mu. So that once this specific rate is predicted, this goes to the differential equation, this ordinary differential equation, very simple, dx dt equals mu times multiply x, so that an ODE integrator can, based on the initial value and the predicted mu each time, can get the x values. So this is known as the solution of the differential equation. But you are still using, in inference time, a differential equation. So basically, a classical hybrid model is a system of differential equations where some parts of this differential equation are a black box model, usually a neural network. On the contrary, the physics-informed machine learning, for example, physics-informed neural network PINs, what they do is they directly learn not the specific rate, so the mu, they would directly learn how the cell grows over time and over pH in this simplified example. And what's the advantage? So for example, in upstream, probably you would not see a big difference or advantage between PINs and hybrid model. But now, for example, imagine that in chromatography, you're comparing a hybrid model where basically you have a system of partial differential equations explaining convection, dispersion, diffusion, binding, and the neural network is only predicting, for example, an isotherm term, so how the protein has affinity to bind. But once the neural network is predicting this isotherm term, you still use the full partial differential equation machinery. So you need to do all this time and X discretization, which is relatively expensive. On the contrary, a physics-informed neural network would directly predict the chromatogram over time. So this is the big advantage. And also, if I can use a very silly example, but I use it a lot in conferences when I introduce this technology, is that imagine that you get a new dog, you bring a new dog home, and you have to educate the dog. So, for example, you might not allow your dog to jump into the sofa because it can break it makes it dirty, etc. The dog doesn't really understand that why you don't allow him to jump into the sofa. But how it learns not jumping into the sofa is because when it does that, you punish the dog, and when it behaves well, you reward him. So with iterations, eventually, the dog learns what is right and what is wrong, so that even if you're not at home, in theory, the dog shouldn't jump into the sofa. So this is the same concept with PINs, which is during training, we use physical, like partial differential equations with the hope that once the model is trained, and here it depends a lot on how you train, so this is a bit picky. So the concept itself is simple, but the implementation is a bit more complex. Ideally, once it's trained, you don't need the physics anymore, so you can compute way faster.
And from what I understood, it seems that on the upstream side, the physics-informed AI and hybrid model are comparable. Obviously, there are some differences between or complementary, versus in the downstream, hybrid modeling only describes a small part of it. And with the physical informed AI, with all the differential equations, you can create models that are much more sophisticated and characterize the whole physics or chemistry that's going on.
So far, the research we have done is we see most value in downstream. So for example, So the father of these technologies, Professor George Karniadakis from Brown University, and we actually collaborate with them. So for the upstream use case, we gave them the task of describing a bolus shot cell system with these pins. And in parallel, we use an advanced hybrid model, which is called neural OD, but basically it's a hybrid model that is more efficient to compute because it uses automatic differentiation. And we saw that actually the neural OD worked better. It was easier to train, etc., than the physics-informed neural network. But on the contrary, we are seeing like the opposite. We are seeing more benefits in downstream when we compare physics-informed neural networks compared to hybrid models.
Ignasi is already reframing how we think about digital twins, and there's much more ground to cover. In part 2, we keep digging into the practical realities of building trust in these models and where the real value shows up for biotech teams. If you're enjoying the conversation, please leave a review on Apple Podcasts or your favorite platform. Thank you so much for tuning in, and I'll see you next time. All right, smart scientists. That's all for today on the Smart Biotech Scientist podcast. Thank you for tuning in and joining us on your journey to bioprocess mastery. If you enjoyed this episode, please leave a review on Apple Podcasts or your favorite podcast platform. By doing so, we can empower more scientists like you. For additional bioprocessing tips, visit us at smartbiotechscientist.com. Stay tuned for more inspiring biotech insights in our next episode. Until then, let's continue to smarten up biotech.